Well, what we are doing, we are just trying to figure out how the intelligent compaction works. And what we have done, we have embedded velocity transducer, geophones, and load plates, pressure plates at one location. And then we have instrumented roller to measure the vibration of the roller and the load that the roller applies, as well as the intelligent compaction measurement values simultaneously. And the two systems are communicating with each other so that we know the distance between the roller and the sensors that are embedded into the ground.
An intelligent compactor to measure the compaction effectiveness of the roller in a section of subgrade. Now, to do that, we are going to install a couple of sensors in the roller itself that we're going to be monitoring continuously, and we're also going to be installing sensors within the soil that are going to allow us to perceive how much the vibration of the roller impacts the soil as it gets closer to my sensor and as it moves away. So the concept is actually to be able to measure the vibration with three systems in essence. One of them is already in place by the manufacturer. It's an intelligent compaction unit that utilizes a sensor of their own. So we're going to be using those two numbers from the manufacturers themselves. And then our two sensors that we have are two accelerometers that measure also the vibration of the drum as it moves along. And in that case, we're collecting that information continuously. But I know we're using the fundamental frequency of the vibration along with the second harmonic. With those two values, we can determine the CMD value. So then we can do a comparison between what the manufacturer is giving us as well as the number that we calculate. And not only that, but then we're going to be doing testing at different points of the section to give us values of stiffness of the soil. Basically, it's going to be modulus of the soil. We're going to be using two instruments to do that. We're going to be using a DCP and an instrument that is called LWD, which is lightweight deflectometer. DCP is dynamic compenetrometer. And we're going to be combining all this information to generate maps that basically we can do a comparison between the stiffness that gets generated by the point data information as well as the information that we collect with our sensors, with the manufacturer sensors, and do a comparison and hopefully have everything look similar. And one of the things that is important is that we can synchronize everything as far as that everything gets aligned, because that's one of the issues sometimes that we end up having problems with. That keep in mind, we're like looking at three different sets of data. One of them is going to be static. I'm going to be collecting data from those geophones. The static's not moving, and then the two that are moving within the roller. So sometimes because of timing considerations, we end up with offsets in time or even location. You know, we're using GPS as a means to try to synchronize everything. So.
That side went well. Let's see what that side, Everything is going smoothly. Sure. We are doing it at MnROAD because, the sites are very convenient. MnROAD, the people are the most hospitable to the researchers. And we have had a long-term collaboration. Well, we are doing it as part of the national project in the National Cooperative Highway Research Program, NCHRP project, and it would impact virtually all the 50 states because that's a AASHTO-driven project.